So now using what we know regarding calculating probabilities and areas under the curve for two different distributions, the standard normal and the t-distribution, we're going to begin to apply this to the idea of hypothesis testing, which is probably going to be the most used thing that you'll take away from this course. So we're going to start with a few definitions so you're able to understand the parlance of this particular topic. And first thing we're going to do is define what's known as the null hypothesis. And that's the hypothesis that sample observations that you will gather from an experiment are purely from chance, or that basically what you're trying to show is not true. So it's maintaining the status quo. If you want to show that taking a drug changes somebody's blood pressure, the null hypothesis that you'll start out with is that the drug will not change your blood pressure. Now we're next going to define what is also known as an alternate hypothesis, or HA for short. This is the idea that is the hypothesis that the sample observations that you're finding are influenced by a non-random cause. So using the example I just mentioned, with a drug having an effect on blood pressure, your alternate hypothesis would basically be that the changes in blood pressure you're seeing are not due to random chance, but instead due to the effect of a drug. And we can actually use statistics to test these hypotheses, and there are basically two results that are possible. The first is we reject the null hypothesis. We say that it's not true, or we fail to reject the null hypothesis. That's not the same technically as accepting the null hypothesis. We generally say in statistics that we fail to reject the null hypothesis. So what's the interpretation of rejecting the null hypothesis? So when you start out an experiment, you always assume that your null is true, that whatever you're trying to show is not going to have an effect. And that really puts the burden on the alternate hypothesis to disprove it. And then the next question is, if we always assume the null hypothesis is true, we test the null hypothesis or possibly reject it by asking the question of, what is the probability of a result that is more extreme than the observed result that you see? And if that probability is lower than some threshold value, and generally in biomedical sciences a common threshold value is 0.05, then the null hypothesis may not be true. So then you would reject the null hypothesis. And one way to think about this is that if the probability of finding what you observed was very small, like less than 5% relative to your null hypothesis, and you assume that it's true, but you've done the experiment a whole number of times, that might suggest that the null hypothesis is not true, which would lead to rejection. So this then leads us into the idea of errors in hypothesis testing, and more definitions, unfortunately, before we get to examples. And the first definition is what's called type 1 error. And it's the idea that you would reject the null hypothesis even though it's true. And the probability of making a type 1 error is called significance, and it's generally denoted with alpha. And so this threshold alpha is generally set at 0.05. And then next there's what's called type 2 error, which is not rejecting the null hypothesis when you probably should. The probability of not making a type 2 error is called power, which will be denoted with beta. We'll go into these with much more detail when we talk about power analysis in subsequent lectures, but just so you have an idea of what I'm talking about when I mention type 1 or type 2 error. So how do we actually begin to do a quantitative analysis and hypothesis testing? So what we're going to do is define what's called a p-value. And that is the probability of observing an occurrence that is at least as extreme as a given test statistic. So if our p-value is less than our preset significance of alpha, then we reject the null hypothesis. If it's greater than alpha, we cannot reject the null hypothesis. And now there are also different types of tests that can be used, or can be performed. The first one is a one-tailed test, where a rejection region, or this p less than or p greater than alpha, is only on one side of the distribution. For example, if your null hypothesis is that some mean that you measured is greater than 10, is greater than or equal to 10, you would only reject the null hypothesis if your mean was less than 10. So if this distribution on the right is like our example distribution for this test, what we do when we do hypothesis testing is we calculate a t-critical value, much like we did with the example of in the previous lecture. And then, so the area to the right of it, the area to the right of a t-critical value is generally given as your significance, or is, in this case 0.05, your alpha. And if your what you're going to do is you're going to compare your t-statistic that you calculate to a t-critical value, and if it lies to the right of this t-critical value, you're in with what's called a rejection region, which we'll talk about more in detail. So this is an example of a one-tailed test where you have a critical value and the rejection is only in one direction relative to that critical value. Now there's also a two-tailed test where a region of rejection is on both sides of the distribution. So an example of this would be if your null hypothesis was just that a mean was equal to 10, you would reject if your mean was either less than 10 or greater than 10. So it's what's called two-tailed. And so for that example, rejection occurs either on either side of the distribution. And whereas before we had an alpha of 0.05 up above with a one-tailed test, we still have a total alpha of 0.05, but it's just split into two sides. So to the right here is 0.025, and to the left of this threshold value is 0.025. It still sums to 0.05, but that's where your rejection region would lie. So you can see that right here. So one example of a hypothesis test would be against a known mean. You do an experiment and you're comparing the results of your experiment against what's a known population mean. And so there's basically three different possibilities that you could have for your mean, or for your hypothesis testing. The first is that would be a two-tailed test where the null hypothesis is that the known mean, mu, is equal to what you observed, mean of big M, and the alternate would be that it isn't, which would make it a two-tailed test. The other one would be that your mu is greater than or equal to what you observed as your null hypothesis, which would have your alternate as just mu is less than M, which is a one-tailed test, and the flip side here where it would be mu would be less than or equal to M, and the alternate would be mu is greater than M. Our t-statistic doesn't change for this. It's still your observed mean minus mu divided by the sample standard deviation divided by the square root of n, with n minus 1 degrees of freedom. So all of that might have been a little complicated to explain without an example, so we're going to go over an example hypothesis test. And so the problem reads as follows. You have developed a new synthetic material for implantable hip joints and want to test this material's elastic modulus relative to that of the current standard material in practice, which has an elastic modulus of 50 megapascals. After an initial round of testing, you have the following elastic modulus values for your new material in megapascals: 52, 63, 57, 54, 48, 52. And you're going to want to test whether these values are what are called statistically significant from the standard. So the first step is proposing null and alternate hypotheses to test if your new material has a higher elastic modulus from the current standard. So my null hypothesis would be that it doesn't. The changes I made did not have an effect, so it would be mu new, so the mean of my new material is less than or equal to 50 megapascals. The alternate, which is what I'm trying to show, is that it does improve upon the elastic modulus. And so the alternate would be that the new material has an average elastic modulus of higher than 50 megapascals. So you should be able to see that this is a one-tailed test, and we'll be utilizing that going forward. So then what we want to know is there a statistically significant difference between the new material and the standard, assuming an alpha of 0.05. So what do we know? Our n is 6, which from that we should use a t-test for our analysis, as the n is less than 30 and the population variance is unknown. So first let's calculate the mean observed elastic modulus, so we can calculate our t-statistic, and that's pretty straightforward, just like you've seen in arithmetic classes for calculating the mean. Our sample standard deviation, which I'll leave you to calculate, is 5.1640 megapascals, and our degrees of freedom is just the sample size minus 1, so 6 minus 1, or 5. So let's calculate our t-statistic. This is the equation we used right here, and we're going to plug everything in. X bar is 54.333. Our mu that we're going against the known mean, is 50. And then our denominator is just 5.6140, which is the sample standard deviation divided by the square root of 6. So we get a t-statistic of 2.056. So so we're gonna keep that information, and then the next part of the way that we figure out whether there's significance is we know that there's a threshold value where the probability of getting a t-value greater than what we calculated is 0.05. So this is the t-value, the t-critical value that's associated with our significance of 0.05. So we find that using a t-table, which we see right here. So the way in which we go about doing this is very similar as before. This is the same table we used for our t-test example. So we go down to find our degrees of freedom, which is 5, and then go over to find a probability, or find our the t-value associated with our alpha of 0.05, and that right there is 2.015. So if this plot on the left here is our standard t distribution for the elastic modulus values, the first thing we're going to do is mark off where our t critical value is. It's 2.015. In the area to the right of that, so in mathematical speak, the area under the curve of the t distribution, starting at the t critical value and going towards infinity, is alpha. So this area under here is alpha, or 0.05. So that's what's called our rejection region. If the t-value we calculated is to the right of this t-critical value, it lies within our rejection region. So what was the t-value we calculated? It was 2.056. And so that lies within our rejection region. So we can safely say that we can reject the null hypothesis. But to go a little further and a little deeper and give you some a little better understanding of what that means, let's think about it. So we said that we reject the null hypothesis when p is less than alpha, and in this case alpha is 0.05. So the p-value is the area under the curve starting at our t-statistic and going towards infinity. So in mathematical speak, it's the integral starting at our t-statistic and going to infinity. So if the area under the curve starting at 2.015 was 0.05, if we started integrating at 2.056, you could see that the area under the curve would be less than 0.05 because we are not including this part between the two dotted lines here when calculating the area under the curve. So when we say reject the null hypothesis if p is less than alpha, that's the exact same thing as saying that our t critical value is smaller than our t statistic, and in this case that's true. Our t statistic is 2.056 and our t critical value is 2.015. So we can say that we can reject the null hypothesis, and that there actually is a statistically significant difference between what we've done, or the material we've made, its elastic modulus, and the current standard. And so what that's saying is that we assume the null hypothesis to be true. And assuming that's true, we've run our experiment, and the odds of getting the value that we've gotten for our experiment are less than 5%. Yet we've run the experiment 6 different times. And so what that's saying is that the odds of, if we've run the experiment 6 times, and the odds of getting these results are, as you can see on the distribution, less than 5%, then maybe the null hypothesis is not true, and that's why we reject it when it lies to the right of our t-critical value. So we've done a one-tailed test. Now let's look and see what would happen in a two-tailed test. We'll use the same example as before. Now we're just going to test if there is a difference or if there isn't a difference. So our new material doesn't necessarily have to be better, just different. And so we rewrite our hypotheses, where the null hypothesis would be that my new material has the exact same elastic modulus as the standard, and the alternate is just different. It's not equal to 50. So our t-critical value is going to change. We'll still use the exact same degrees of freedom, so it'll still be 5 degrees of freedom. But instead of looking on the t-table for 0.05, what we're going to do is look at 0.025, or this area right here, because for a two-tailed test, remember, the two tails have to sum up. The two tails will sum up to 0.05. So we have to use the t-critical value, not for 0.05, but for 0.025. And you'll see that when you use a t-table for this, if you summed up this area and this area, you'd still get 0.05. And so when we do that, when we go back to our t-table, which is right here, if we start at degrees of freedom of 5 and we go to 0.025 instead, our new t-critical value becomes this right here. Let me use my pointer. Becomes 2.571. Okay, so let's go back here. So 2.571 is our new t-critical value. Our t-statistic that we calculated stays the same at 2.056. So our t-critical value is greater than our t-statistic. So if our t-critical value lies right here, and our t-statistic, say, is right here, then our p-value is actually greater than alpha, so we cannot reject the null hypothesis. Now similarly, there's all sorts of different t-tests or hypothesis testing for different scenarios. I'm going to present just a few equations without an example, but it goes in the same line of thinking for a difference between two observed means. So instead of comparing an observed mean against one singular known value, this is between two, testing for the difference between two means. So you're comparing two measured means. The process stays the same that we go through. We define our null hypotheses, we calculate t-statistics, and compare them to critical values, but the equations change slightly. So there's three possibilities again that are mu1. Let's say we have observation 1 and observation 2. The mean of 1 minus the mean of 2 is equal to some difference d, would be our null hypothesis. And our alternate is that it would be not equal to d, and that's for a two-tailed test. And you can see here how you get one-tailed tests with these two sets of null hypotheses and alternate hypotheses. Now note, if d equals 0, your null hypothesis just becomes one observed mean is equal to the other, and the alternate is one observed mean is not equal to the other for a two-tailed test. And the equations go as follows. It's still a difference in observations. It's just for the t-statistic, it's x1 minus x2, the means, minus the difference. And if it's 0, then you would just discount that over some sort of standard error. Now, the standard error is not just the standard deviation divided by the square root of n. It's changed a little bit, as you can see. And the calculation for degrees of freedom is not just something, it's not just n minus 1 anymore, it's this equation, which is kind of messy, but able to be calculated if you know the standard deviations and the sample size of both sets of data.